So non-homogeneous, linear, order n, that means your highest guy right here has an nth derivative. And I went ahead and did something a little bit different than what we've done in the past, which is I went ahead and said, notice here, let's make this leading coefficient 1. Notice if you don't have 1, you can always force it into this term by dividing whatever that coefficient is by every single term in the equation. And when I say coefficient, remember our coefficients here include your independent variables. So if this had been an x times the nth derivative, you can divide by x. And it changes some of your domain issues, but we'll deal with that later. Actually, we're totally going to hand wave through that for the rest of the semester. Now, next thing that we have is the associated homogeneous differential equation. Notice everything's the same except the one term that had no dependent variables was 0. This is the same as what we've done previously when we dealt with non-homogeneous differential equations. And again, same thing that we've done in the past. Y with a subscript p indicates a particular solution of your non-homogeneous differential equation. Y with an h is the general solution of the associated homogeneous differential equation. And the general solution of the non-homogeneous differential equation is where you add those two guys together. So this is, you take one of the solutions that you find, however you find it, add it to the homogeneous solution, and bam, that actually gets you a general version of the solution for the non-homogeneous guy. All of this is exactly the same as what we've done so far, as long as we've been talking about non-homogeneous stuff. None of that is going to change. Here's the only part that's going to change. Instead of using method of undetermined coefficients to find our particular solution, we're going to use variation of parameters to find your particular solution. And that's literally the only change now, is to use a different method to find the particular solution. You could totally guess and check to find your particular solution. Please don't. Method of undetermined coefficients is kind of like guessing and checking, but being a little bit strategic about it. Okay? Variation of parameters is actually going to have a formula that you compute. So here's the actual method. Well, I lie. This is almost the actual method. This is the outline of the algorithm. So first thing is, for your method of variation of parameters, you have to have a non-homogeneous differential equation. You can use the method of variation of parameters anytime you have a non-homogeneous differential equation. We're going to only be dealing with linear, and you're going to have to use variation of parameters if your method of undetermined coefficients fails. But every time method of undetermined coefficient works, you could totally have used variation of parameters too. So this is a method that works more frequently than undetermined coefficients. However, for many people, it takes longer to do than undetermined coefficients. So there's pluses and minuses. If you haven't looked at the, I hate to use the word paper, homework set for this section, one of the questions on there is actually going to have you work through a differential equation twice. One would be with undetermined coefficients, the second one would be variation of parameters, and it'll ask you to do an analysis. Hey, which of these seem to work better on that differential equation? Okay, so there's lots of times when both of the two methods would be perfectly fine and you get to choose. Now, you have to use variation of parameters in the cases where undetermined coefficients fail. So your non-homogeneous part of your differential equation isn't one of those three formats for undetermined coefficients, or your differential equation doesn't have constant coefficients. Undetermined coefficients only will work if you have the constant coefficients on your y, y prime, y double prime, all of your dependent variables or derivatives of dependent variables. Okay? As soon as you have even one guy that's not a true constant, so it's like an x times y prime, still linear, but now you have to use variation of parameters. All right, so that's how to decide when to use variation of parameters. So to remind ourselves, there's our non-homogeneous linear differential equation. If we pull All right, see if you guys can hear me now. Excellent. Sorry about that. I'm not sure why it happened, but I had to restart my mic. All right. So what was the last thing you guys heard? Something about associated homogeneous solutions? Okay, so I was just going over stuff we've done before. So this here is non-homogeneous linear differential equation, same format we had on the previous slide. This one here was our associated homogeneous solution, and a reminder ourselves the y with subscript. Those were those individual solutions that we found from the roots of the characteristic equation. Caveat, that only is going to work in our class if we have the constant coefficients on the y, y prime, y double prime, etc. Okay? If we don't have those constant coefficients, we haven't talked about how to find these specific solutions to your homogeneous differential equation, so I would have to give you those solutions. And you will see questions like that, okay, where somebody says, hey, these three functions are your solutions to your associated homogeneous differential equation. Now go find your variation of parameters, particular solution. Okay. All right, so that's associated homogeneous. Now, here's why we put the associated homogeneous solution up. This is the format for our particular solution with variation of parameters. Okay. This one here says your particular solution. Notice it's some function that we're going to call U1 times the one of the homogeneous solutions. Then you're going to have y2, again, some function. Maybe it's a constant. Maybe it actually has your independent variables in it, multiplied by another one of your homogeneous solutions, and you keep going. So notice these two guys here, your general form of your associated homogeneous solution, and now a particular solution have almost the same format. The only difference is with the homogeneous solution, you truly have constants like 2 and 3 multiplied by each of those solutions, y1 through yn. But the particular solution, you're going to have at least one of these u guys not to be a true constant. They would actually have the independent variable in it. And we're going to see how to find those in just a second. Here's the interesting part about this type of a particular solution, or this format of the particular solution. It turns out it doesn't matter what your differential equation is, linear, non-homogeneous differential equation, you're always going to be able to find a particular solution of that format, which means variation of parameters always works. The only holdup that we're going to have with variation of parameters is because linear algebra is not a prereq for this class, we're only going to go up to order 2 for the formula for variation of parameters. That is 100% just because we don't have a prereq of linear algebra. A couple of you who have it, I may post something to show you what the true formula is in any of order whatever you want, not just order 2. But for the rest of you, this is what you got until you need it in the future differently. Okay. So here's actually what you do. Okay. We're going to build our particular solution in the following way. First thing we're going to do is we're going to find all of those little solutions from our associated homogeneous equation, same way we would have done it before. We're then going to compute the Wronskian of all of those little solutions. Then we're going to compute our U1, U2, and I'll give you the exact formula for that in just a second. The formula will be specific to order 2 differential equations. And then we're going to go ahead and build our particular solution. Now, everything that I listed right here in those 4 bullet points, that works regardless of what your order is for your differential equation. You could have a 10th derivative involved, and this method would still work. The only hang-up would be right now, you guys, if you haven't had linear algebra, don't have the math yet to be able to compute those guys, just because the formula gets bigger. Okay. So key things to note, you have to, and I cannot stress this enough, whoever you have tagged as your y1 and then y2 for your homogeneous equation, for your solutions of your homogeneous equation, you have to put it in the same order for your Wronskian. If you swap around the order there, what happens is it'll swap the columns in the matrix that gives you your Wronskian, and that actually flips the sign on your answer to your Wronskian. That'll affect the formula for U1, U2, so watch out. Make sure whoever, and it doesn't matter who, but whoever you've labeled as Y1, Y2 in that order you put them in your Wronskian. Okay. So that's the first key thing. And the second key thing is what we've already said, which is we're only going to do this method for second order differential equations. But I'll plan on posting something so you can see what would happen in higher order too. Okay. Now, here's the actual formulas. So if we look specifically here at a second order differential equation, and here I broke it down just so that there's no little dot, dot, dots. You have everything. Got a second derivative term. Please notice here, there's nothing in front of that derivative, so it is exactly like pretend that was a 1. Wow, that's terrible. Let's undo that. 1. A coefficient of 1, pretend that horrible thing is 1. You then have whatever you want in terms of independent variables times your first derivative, whatever you want in terms of independent variables times your dependent variable, and then your non-homogeneous part. The key thing right here is that 1. Please note, if you look this up in your textbook, your author does not require a 1 right here, so his formulas are going to be a little bit different than what I tell you. Okay. So, variation of parameters. First thing you do is you find your 2 solutions from your associated homogeneous differential equation. We're going to have some examples for this, and all of our examples are going to have to be where we look at the associated homogeneous differential equation, and it would have to have constant coefficients. All right, can you guys hear me now? All right. So what was the last thing you guys heard? I didn't say anything other than reading the things that came down on the slides. The only thing that we ended on, which is when I noticed that you guys said that there was no audio, was what happens if you don't have that leading coefficient of a 1 on your second derivative. Suppose instead of a 1 it was, I don't know, say a 2. How would you get the correct f of x? How would you get the correct non-homogeneous part of your differential equation for the formula at the bottom? Yep. So if you don't have a leading coefficient of a 1 on your second derivative, take whatever's actually there, whether it's the 2 like we just talked about or anything else, and you divide everything by whatever that thing is. So in that example we just talked out, you would divide by 2. This here, that f, is whatever you have for your non-homogeneous part divided by your leading coefficient. So if you don't want to just say that f times whatever, if you want to actually put like notes to yourself of what to remember to do, you would always divide out by the leading coefficient. If your leading coefficient is 1, it's just that non-homogeneous part. Okay? So there's a little cleanup involved here with how I've written these formulas. Honestly, I think it makes the formulas easier to remember, but you do have to worry about the cleanup. Okay? So that's how to find U1. U2's formula is almost identical. Notice we still have an integral. We still have the non-homogeneous part after cleanup. We still have a divide by the Wronskian, and we still have a multiply by one of the 2 homogeneous solutions. Now, here's the key thing. Notice the subscript on the W's. There is no W. a subscript on the U and a subscript on the homogeneous solution is always exactly opposite. Okay? So you can actually, instead of memorizing two separate formulas, you can look at these guys as the same exact format if you remember that the two subscripts on the U and the Y1 or Y2 have to be different subscripts. Now, the only other thing to remember is one of them is positive and one of them is negative, and it matters who's positive and who's negative because that ties into the order that the functions are plugged in to get your Wronskian. You have to have the negative as part of the formula for U1. So you take these two formulas that you compute for your U1 and your U2. What do you do with it? You multiply each of them by Y1 and Y2, and that then gives you the formula for the particular solution. Notice you can also go ahead and plug these in all together, and if you plugged it in all together, this would be negative Y1 integral f times Y2 over the Wronskian plus Y2 non-homogeneous part times Y1 divided by the Wronskian inside the second integral. Please, 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 if you do it that format, and that's totally fine to do it in this all put together at once formula right here, you want to make sure that your Y1 and your Y2, the one on the outside, the one on the inside, have the opposite subscripts. Okay? You also want to make sure that you do not multiply your homogeneous function, the Y1 or the Y2 here, inside the integral. You must compute the integral first. And that's one of the reasons that I would recommend at least the first 1 to 10 times that you do these questions of these type, compute your U1 and U2 separate, and then compile the answer together for your particular solution. Okay? So that's the idea behind variation of parameters. It is literally just a formula for your particular solution. Everything I got left for today is just going through some examples, and I've got 3 examples prepped up for us. So any questions before we get going on the examples? All right, seeing nothing from you, let's jump into some examples. So the first example that I've got for us is this guy. So we want to find the general solution of a differential equation, a non-homogeneous differential equation. We've got the second derivative of y plus 9 times y equals 2 times the secant of 3x. Now, when we look at this guy, we can do the exact same procedure that we did when we've been dealing with non-homogeneous differential equations for the past however many days it's been. Okay? So step 1, and I'm just going to go ahead and circle this as step 1. We want to go ahead and find, let's do an F for find. That might help. So find our associated homogeneous differential equation. In the method of undetermined coefficients, I recommended that you go ahead and you do this first, but technically you could have swapped the order of whether you find the particular solution first or the homogeneous solution first. With variation of parameters, there is no swapping. You have to find the homogeneous solution first because parts of the homogeneous solution are going to be in your formula for your particular solution with variation of parameters. The first thing you do is we look at our associated homogeneous differential equation. So we're looking at the second derivative plus 9 times y equals 0. We look at our characteristic equation. So hopefully you are all thinking y squared plus 9 equals 0. Remember the conversion. The y turns to an r and the derivative turns into the exponent. So y is not the derivative, so it's really r to the 0. Then we say we need to solve for r. This one here, if you solve for r, will turn out to give you 2 answers, and it's going to be plus or minus, specifically plus or minus 3i. Okay? And yes, I skipped some steps with that one. Not many, but a couple. Now, once you have your roots, what can we do next? What would we be finding next? In other words, what would be the 2 functions associated with these roots? Yes, we should totally be looking for a y1 and a y2. And you guys let me know, what do you think they should be? Remember, the roots are imaginary here. So if you have imaginary roots, what's the key thing that comes out with imaginary roots? Huh? Oh, we've got that part already. What's the function going to look like? So say you're working on web work, and you've already entered the roots at being plus or minus 3i. And it says, all right, well, what's your y1? What is your y2 equal? What should we be looking for here? Though I don't think it actually splits it up in that way too frequently. It normally just asks you what is now the solution of the homogeneous differential equation. In other words, are we going to, ooh, there's somebody. Yes, so the format, if you have imaginary roots, is e raised to the alpha times whoever your independent variable is, in our case x, good, times sine or cosine of beta times x. Now, you said cosine, so let's go ahead and write cosine as y1, so cosine of 3x, which means that y2 has to be who? So y2 in this case has to be exact same format, except you swap out the cosine for a sine. Now, here's the fun part. It doesn't matter who you pick as sine and who you pick as cosine. You do have to have one of each, and it now has to stay consistent. In our case, y1 will now be cosine of 3x, and y2 will be sine of 3x. You could solve the same problem and get the same exact answer if you flip-flopped them, but again, you have to stay consistent. So this tells you that your homogeneous solution would be some constant, say C1, times your first function, plus some constant, say C2, times your second function. And technically, you don't need the parentheses around 3x, but it makes it easier to see. Now, key thing, throughout the entirety of this problem, or this question, we are going to be using our y1, y2. Okay, so I'm going to box them to make them easier to see. Step 2. So step 2 has been to find our particular solution, but with variation of parameters, you have to do a first step, okay, or a preliminary step before we jump into our particular solution. So I'm going to call this guy 2a. Okay? In other words, we want to compute the Wronskian. So in our case, our Wronskian is going to be w. It's going to be our first function, our second function. You have to make sure y1 comes first. And then second row is we'll take the derivatives. So in our case, I'll do the easy step, which is the top row. You guys think about what you need to put in the second row. So we'll have cosine first, and then we'll have sine. So what should I put in that second row? What should be in the first entry of the second row? So derivative of cosine of 3x, the negative sine of 3x. And what about the last spot? Oh, yep. So here, derivative of sine 3x will be 3 cosine 3x. And now we're ready to go ahead and compute this guy. So to compute the Wronskian, we're going to multiply down the diagonal. So this would be cosine times 3 cosine, or 3 cosine squared of 3x. And then we're going to subtract when we multiply up the off diagonal. So that'll be our sine and our negative sine, except I forgot something. You guys totally said it correctly. I just missed it. That derivative under cosine should have been negative 3 sine 3x. That was just me missing the 3. Okay. So when we multiply up that off diagonal, we'll get the negative 3 sine times regular sine. So this will be negative 3 sine squared. And of course, the two negatives there are going to turn into a positive. Well, if you have 3 cosine squared plus 3 sine squared, what's that going to turn into? Anybody have a guess? So I'll do the middle step and then we'll get to our answer of 3. If we pull a 3 or factor a 3 out of both of these terms, you'll get cosine squared. The two negatives turn into a positive. You factor a 3 out of the last term, you'll get sine squared. And notice cosine squared plus sine squared totally equals 1. And that's always true as long as, here's the caveat, the stuff plugged into the sine and the cosine have to match. So the two angles have to be the same. If you had cosine squared of 3x plus sine squared of 2x, you can't actually combine them together like this. Okay. So that tells us our Wronskian is 3. So here's what we've got so far. We've got what y1 equals, got what y2 equals, and we also have what w equals, namely our Wronskian equals 3. And we also have, quick check, if we come back up here to the differential equation, can't find my cursor. There it is. If we come up here to the differential equation, we have a leading coefficient of 1, so that means this guy right here, the 2 secant, that is our f that we'll use in our formula. Okay. So I've run out of space on this page, and I'm not going to try to fit it in there at the very bottom. So let's go to the next slide, which is currently totally blank, and we'll finish this guy off. Okay. So here's what we know so far. We know that y1, I'm now wishing I typed this part, is cosine, y2 is sine. We computed the Wronskian, it was 3, and our 2 secant is our f from our formula. Okay. So now we are ready to do 2b, and this is find variation of parameters, method of finding your particular solution. Now, quick check. In this example, you have to use variation of parameters. You cannot use method of undetermined coefficients. Why is that the case here? And while you guys are thinking about why you have to use variation of parameters, I'm just going to copy down the formula for y1 and y2. Not y1, u1 and u2. I guess I'll just do one at a time. So this non-homogeneous part, not in the right format for undetermined coefficients, because, why? The trig function, is it either sine or cosine? What do you guys think? Is our non-homogeneous part either sine or cosine? Yeah, don't overthink it. If it doesn't exactly match sine or cosine, you're not going to be able to use undetermined coefficients for this example. You're going to be forced into using variation of parameters. So if we go ahead and apply variation of parameters, the next step in finding your particular solution is you need to go ahead and find your u1 and u2. So I went ahead and wrote down the formula for u1. It's the integral non-homogeneous part times the opposite subscript solution that we found previously divided by Wronskian. And then the dx here, you match the x to whatever your independent variable is. So our next example, I've got t to show you how that would change. So here, still have your negative, we'll have the integral. The f, so the non-homogeneous part, is 2 secant of 3x. Our y2 is sine of 3x. And then we divide by 3. So the hardest part of variation of parameters is remembering your integral rules. Now, I on purpose picked trig functions because trig functions are the ones that get, let's face it, the most complicated. Okay? So trick here with trig functions is, and I guess is what the trick is that I'm about to tell you. Well, the first thing is I'm going to pull the 2 and the 3 out front. But then you still have secant times sine. Ooh, yes, you can totally rewrite that as tangent. So if secant is the same as 1 over cosine, so if we write this out, sine would stay on the top, and secant would be 1 over cosine, or cosine would be on the bottom. Now, I'm not actually going to write it as tangent, although you totally could. And if you actually know the integral of tangent straight off, go for it. At our school, we don't normally have the integral of tangent being one of the integral rules that you've been asked to memorize back from Calc 2. So, can I assume that you guys don't have the antiderivative of tangent memorized? Would that be a correct assumption here? Although if you do, that's awesome. Okay, I got a couple of you confirming that. If you do have the integral of tangent memorized, awesome. But if you don't, here's how you find it. Okay? So what I'm going to do is I'm not going to write it as tangent. I'm going to keep it as sine over cosine. If you wanted to compute that integral, any guesses what trick you would use if you have cosine on the bottom and sine on the top? Yep, you're totally going to do substitution. So I'll write down the substitution. It's going to be u equals something. What's our u in this case? I'm now regretting a u, so maybe let's do a v because we already have u's involved. What do you want to be your substitution? Yep, definitely do cosine, and specifically make sure to include the cosine 3x, the whole thing. All right, so you then take the derivative of this guy, and we've computed him before, so I'm just going to write it out. So we've got negative 3 sine of 3x. Don't forget the dx at the end. Now, what's awesome about picking cosine as your substitution? Notice the derivative here, it's totally already in our formula. So when we convert over to u, ignore the coefficients unless you want to deal with them right now. But what are we going to get in terms of the u's in this integral? I'll leave a space to put the new coefficient we need to worry about. So what would happen? The sine and the dx are going to turn into your du. The cosine, I shouldn't say that, it's a v. The cosine is going to turn into your v, so you get something that's 1 over v, except there's an adjustment factor. So what's the adjustment factor going to be here? In other words, what coefficient are we going to worry about having popped into existence when we convert over to v's? Yep, so you're going to worry about your negative 3 right here, and specifically make sure it's the reciprocal, so you divide both sides by your negative 3. So we're going to have an extra little factor out front of negative 1/3, and technically speaking, when you multiply by a negative, you should put that in parentheses. Now this is somebody that we can totally compute. We'll put it up here to indicate where we're going. So this is 2 over 9 out front. And then what would be the antiderivative of 1 over v? Anybody got that? Hopefully you're all thinking that 1 over v converts into a natural log. So we'll have natural log of v. And it turns out we're not going to need the constant, but I'll go ahead and put the constant here at the end. And I put the C3 there just because we've already used C1 and C2 when we wrote up our homogeneous solution. So we'll go ahead and finish this off. And to finish this off, we get that U1 equals 2 over 9, natural log of, find your V, which is cosine of 3x. Don't forget the absolute value because I almost did. 3x, C3. And then we have to do it for U2. So writing out the formula for U2, this would be, don't put a negative out front. So this would be integral f times y1 all over the Wronskian. So notice the only thing that's going to change in your integral is we're not going to pull y2, which was sine. We're going to pull y1, which is cosine. Not going to lie, this one's the easier of the two. So non-homogeneous part is 2 secant of 3x. Wronskian's still 3. And now y1 is cosine of 3x. And what is absolutely awesome about this integral? Anybody spot what's amazing about this integral? Because all the stuff inside the integral is going to simplify. You got it. What's awesome about secant times cosine? Secant times cosine is going to equal 1, which means the only thing left inside of this integral is going to be 2 over 3. And we can compute 2 over 3. It's just 2 over 3 times x plus some constant. And since we've already used a C1, C2, and C3, I went ahead and wrote C4. Okay? Now, we want to put this all together. And putting this all together, according to variation of parameters, your particular solution is y1 times u1, y2 times u2. So if we put this in, the u1, where'd u1 go? This is 2/9 natural log of cosine 3x, all multiplied by, I forgot the C3, all multiplied by cosine 3x. And then u2 was 2/3 x plus C4 times sine of 3x. Now here's the fun part. And I'm about to have to go to the next slide because we've used up all the work here. Okay? So I'm going to recopy the homogeneous solution that we found previously and the particular solution, and then we're going to put it all together. So our homogeneous solution was C1 cosine 3x plus C2 sine of 3x. Our particular solution that we just found was 2/9 natural log of cosine 3x plus a C3 times cosine of 3x plus 2/3 x plus C4 times sine of 3x. Now, how do we find the actual solution to this non-homogeneous differential equation? Don't overthink it. Nope, you just add them together. So this is going to be YH plus YP. Now, here's something to know. When you're doing variation of parameters, I'm going to claim that you're never going to need these constants from your integration. You're never going to need the C3 and C4. Here's why. So you've got C1 cosine of 3x plus C2 sine of 3x. That's from your homogeneous solution. Now I'm going to multiply out these two things right here, or distribute the cosine and the sine through. So this means we're going to get 2/9, and it's formal, it's official to put the cosine in front of the natural log. So this would be 2/9 cosine of 3x natural log of cosine 3x. And the next term, when you distribute through, would be C3 cosine of 3x. Now, here's the question for you. That last term that's just barely fitting in the slide, why would I say we wouldn't need the C3? In other words, why would I say there's absolutely no reason to have this last term involved? Besides it making the fact that this format right here is not one particular solution, but a whole family of solutions. Besides that fact, yes, your C1 right here and C3 combine to be some new arbitrary constant. So that means you do not need this guy here. It's a repeat of somebody you already have. Okay? Same thing's going to happen with a C4. But let's go ahead and see what happens. So for the second part of our particular solution, we're going to multiply through by sine. So this is going to be 2/3 x sine of 3x plus C4 sine of 3x. Quick check. Does that last term with the C4, is it necessary? Again, it's not necessary because it's totally going to combine with the C2 term that already is a constant times sine of 3x. So this term is also not needed. Okay? So this last part here, those guys are coming from your particular solution. These two guys not needed, which means the two constants C3 and C4 are also not needed. Notice if we went back a slide, that would tell you that right here in all of this work, you can do what every person in Calc 2 always wants to do and not worry about your constants of integration. Now, on the flip side, if you do worry about your constants of integration, notice what happens when you multiply through. You'll automatically have picked up your homogeneous solution. Okay? So there's two different ways to think about it. Questions kind of make sense, at least a little bit so far. All right, seeing nobody freaking out yet, let us move on to our next example. So the next example is somebody where method of undetermined coefficients also doesn't work. So this one here is we want to find the general solution of t times the second derivative of y minus 2t times y prime plus t times y equals e to the t. So differences. This time we don't have an independent variable of x, we have an independent variable of t. There's also another issue that we need to worry about. Anybody spot an issue that we need to worry about straight off the bat before we do any work whatsoever? It's really, really subtle. But it's one of those things that if we don't point it out here, you may or may not miss. Yes, so that's a key thing. Your coefficients in front of the y, y prime, and y double prime are not all constants, which means right now, unless we do something, you don't have a way of finding those solutions to the associated homogeneous differential equation. But I'm going to claim we can fix this. Any guesses how we might fix it to make it in a better format? Yep, I would definitely recommend divide everything by t. It fixes this differential equation in two ways. One way is it makes it so we can actually use the characteristic equation and find the solutions to your associated homogeneous differential equation. And the other way, or the other thing, is it allows us to actually use the formula for variation of parameters that I gave you at the beginning of class today. So here we divide by t. So the first term will turn into the second derivative of y. Don't forget to divide by t on all of the terms. So second term will turn into -2 or minus 2y prime. Divide the third term by t, and you'll get just a plus y. And divide the last term by t over on the other side, and you can either write it as e to the t over t, or you can write it as t raised to the -1 times e to the t. And it doesn't matter which of those two guys you worry about. Now, this does actually change your domain a little bit. In the original differential equation, you could pick t to be any value you wanted. Everything will work just fine. In this associated differential equation, you actually have a situation where t can't be 0. Okay? So sometimes dividing by your independent variable will affect your domain a little bit. In our class, we're not going to focus on that hardly at all, past a couple comments that I give you. But if you work on these guys in the future and you actually care about when t equals 0, then you might have to do a little bit more adjustments. Okay? But for us, this is perfectly fine. So first thing we want to do is look at the associated homogeneous differential equation. So we'll go ahead and find our associated homogeneous solution. So we grab that associated equation. So second derivative minus 2y prime plus y equals 0. Now that it's all constant coefficients, we can go ahead and use our characteristic equation. Please, please, please note, I can't stress this enough. You cannot use the characteristic equation to find the solution of a homogeneous differential equation if there's an independent variable involved. So we'll do our conversion, and our characteristic equation is r squared minus 2r plus 1. We go ahead and we try to factor it because factoring is awesome. Anybody grab what the factors are? Hopefully you're all thinking r plus or minus something. So I got roots. So we've got r minus 1 squared, which tells us one of our roots is, and the other root is, well, they're both the same thing. So our roots here would be positive 1s. And when we pull this over then to our y1 and our y2, anybody grab what y1 and y2 should equal? Similar? So we'll have e to the t. And for y2, anybody grab what y2 is? It wouldn't still be e to the t, because remember we need these to be linearly independent. Okay? So here we've got t e to the t. All right. And that was our fix for linearly independent, which means our homogeneous solution would be some constant times that first answer plus some constant times the second answer. Bam, we got our homogeneous guy. Okay. So key things are whoever you've labeled as your two homogeneous solutions, you have to keep the subscripts the same throughout the rest of the question now. If you flip-flop those subscripts, totally fine, but you have to worry about, well, you have to do other adjustments. So next thing, Wronskian. So 2a. The setup here is you want to make sure that the functions are done in the same order as what you wrote them out in terms of subscripts. So here you've got e to the t and then t e to the t. So out of the easy derivative, which is e to the t, you guys see if you can figure out the derivative of t e to the t. Or perhaps more importantly, how to type it. Anybody got that second derivative we need? And when I say second, I don't mean second derivative, I mean the other derivative. I'll put parentheses while you guys are thinking. Ooh, I love it when they all come in at once. So yep, product rule, we'll take the derivative of the first, which is 1 times e to the t, plus t times derivative of the second, which is still e to the t. So we got e to the t plus t times e to the t, and all the ones that I see coming in look like they're right, just flip-flopped in order. Now, we go ahead and compute our Wronskian. Key thing with your Wronskian is you multiply down the diagonal first. So e to the t times that expression inside the parentheses would be e to the 2t plus t e to the 2t. Don't forget you add the exponents. Then you subtract when you multiply up that off diagonal, and we'll have e to the t times t e to the t. So we'll get a single t and then e to the 2t, which means our Wronskian has to equal what? So our Wronskian here would be simply e to the 2t. And that takes care of finding the Wronskian. Now, before we go ahead and jump into finding the particular solution, let's go ahead and circle all the things we need to. We're going to be using our Wronskian, which is e to the 2t. We're going to be using our two homogeneous solutions. And the other thing that we're going to need is we are going to need our non-homogeneous part of our differential equation. And you guys tell me, which do you think it's going to be? That first one or that second one? Those are your two choices. So you think it's just going to be e to the t, or do you think it's going to be the e to the t divided by t? So I'm getting several answers coming in, and the correct one is this one, and that's because that's the one where you have, going back to where we did our adjustment, that's the one where we have the leading coefficient is 1. Okay? So be careful, it's super easy that if you have a leading coefficient here that's not 1, you grab whatever's written. You do need to make sure you do that little bit of an adjustment. Otherwise, your formulas get weird and crazy, and it may be that you actually can't compute the integral outside of a computer program, or it just might be that it just turned out to be wrong. All right, so let's jump to our next blank slide, and we'll go ahead and start computing the particular solution on the next slide. But we're going to need all 4 of those boxed pieces of information. So I was actually thinking ahead here. And rewrote the differential equation at the top for us. We also had our 2 functions, and let me go ahead and recopy those down. This was e to the t. Second one was t e to the t. And then our Wronskian was e to the 2t. All right, so that's the information we need. The 2b, this is where we find our particular solution. So we're going to want to compute our u. And this one is negative. And then inside the integral, we have non-homogeneous part after adjustment times y2 over the Wronskian. And here, you would integrate with respect to t because t is the independent variable. Okay. If we want to, we could actually set this up for the other one as well. This would be u2 positive integral f times y1 over the Wronskian dt. Here's hoping that everything now fits in there in the appropriate way. All right, so if we go ahead and plug in, negative stays the same, integral stays the same. The f is the adjusted f, so this is t raised to the negative 1 et. Then we have y2. Y2 is what? Y2 is t e to the t. We want to find our Wronskian, and our Wronskian was e to the 2t. Now, anything nice about that fraction? In other words, what does that fraction inside of the integral symbol simplify to? Because it almost always will simplify. Yep, not going to lie. I really like u1 in this case. All right, so we're going to go ahead and simplify that fraction. It'll be simply a 1. So hopefully you're all thinking then the antiderivative of 1 is just going to turn into t. And remember last time we said that we didn't actually need any of those plus constants from the integral. So I'm going to leave off putting in any plus c's here at the end, just because we're going to end up not needing them. So that takes care of u1. Now u2 is going to be done the exact same way. So for this guy, no negative out front. We'll have the f, which is t to the negative 1. et. We're then going to have y1. y1 was et, or e to the t. And then all divided by the Wronskian, which is e to the 2t. Now this one is not quite as awesome as u1 was, but that stuff inside the integral, the stuff in the fraction, also simplifies. Anybody have a guess what it simplifies to? Yep. All of those e's cancel, and you'll just get the e to the negative 1 power. And you should definitely convert your t to the negative 1 into 1 over t. Why? Because it's easier to see the antiderivative. So what's the antiderivative of 1 over t? Hopefully you were all thinking. And that long pause was totally so that somebody could send me an answer. So hopefully you are all thinking natural log of t. And just like, awesome, there was just a lag on my side. And hopefully you can include a plus a constant here, but also totally fine to just leave off the plus a constant here as well. Technically speaking, you do need the absolute values around the t's. The higher up in math you get, the more people will tend to just leave them off because they're lazy. Always remember, though, if you left off absolute values because you were too lazy to put them in, if you start plugging values in and you get natural log of some negative number, go back and check if you actually should have had absolute values there. That's pretty common the higher up in math you get. So, putting this all together, this tells us that our particular solution of y is going to be, I'm going to write out the formula first. So u1 times y1 plus u2 times y2, and now I just plug in. So u1 was negative t. We're going to multiply that by y1. So we have negative t y1. or negative t times e to the t, plus, now technically speaking for the second one, we have y2, which is natural log of t, times, where'd it go? y2 up here, which is t, e to t. It is standard, though, to put the natural log at the end, so I'm going to flip-flop the order. So this would be t, e to the t, times natural log of t. Okay, so that's the particular solution that the variation of parameters spits out at us. Okay? Now, next slide and last slide that we're going to have where we work through this problem is we're going to grab our particular solution we just found, our homogeneous solution that we already found. We'll add them together to get our actual general solution. So to remind ourselves, our homogeneous solution here was C1 e to the t plus C2 t e to the t. Now just copy down that particular solution we just had, which is negative t e to the t plus t e to the t natural log of t. So our general solution for this differential equation is going to be who? What should we do with those two pieces of information we just found, this being really our step 3? Yep, we're just going to add them together. Don't overthink it. So here we've got C1 e to the t plus C2 t e to the t minus t e to the t plus t e to the t times the natural log of absolute value of t. And this guy will actually work for any value except for when t equals 0. Again, that one only works for every value when t doesn't equal 0 as well. And if you actually check the original guy where it had t multiplied over here that we had to divide out by, you'd actually get if t equals 0, a 0 equals e to the t, and e to the t never equals 0. So it turns out t can't be 0 with this differential equation, so no worries in terms of the domain shifting here. Now, this here is a perfectly fine answer, but I am going to claim that a better answer is this one. That the general solution is actually some constant times e to the t plus some constant times t e to the t plus t times e to the t times natural log of t. Anybody have a guess what happened between that last line and the line right before him? Or it? There is a difference. You got it. It's totally these middle terms right here. So if you look at the middle terms right there, both of the middle two terms in the second to last line has that constant C2, so some constant times t e to the t, and then we subtracted 1 t e to the t. So you add those two terms together, and this C3 is actually who? Well, it's C2 minus 1. Okay? This is something that actually happens a lot with variation of parameters, just with how the formula works. You'll often pick up a term in your particular solution that is in fact a term that's taken care of by your homogeneous solution. So way back up here, notice this guy matches that second term right there. That tells you you don't need them. We could have actually just crossed them off right there if we needed to, or if we wanted to. Okay? So that deals with that guy. Questions? Make sense? Kind of feeling okay so far? All right, so those two examples are the two really big examples of what can happen. And I've got one more example, and for this last example, I'm going to abbreviate some of this stuff. So here's the last example. This one here is the initial value problem. It's got some guy right here, second derivative plus 2 times derivative plus the original dependent variable equals e to the negative t. This is somebody that variation of parameters will always work, but this is somebody that method of undetermined coefficients will also work on. y, all constant coefficients here, and over here is a perfectly fine term for your non-homogeneous part for that method of undetermined coefficients. We also have some initial conditions which are new. So here's where I'm going to abbreviate. First thing I'm going to abbreviate is finding our homogeneous differential equation. At this point, we've done this tons and tons, so I'm just going to tell you what the two terms are. So the first function here from the homogeneous part is going to be e to the negative t, and the second one is going to be e to the negative t times t. It actually turns out, when you grab its characteristic equation, to be almost identical to the last example we had. The only difference here is a plus instead of a negative, which converts your exponents up there. Okay? And I'll post this full solution, so if you want to look over how we got this, you totally can. Second thing that we're going to need to worry about doing is we're going to want to worry about finding our Wronskian. Again, those two functions are almost identical to the two functions that we had in the last example. So I'm going to go ahead and just give you what the Wronskian is right here. So our Wronskian here should be e to the negative 2t. Notice with our functions only have changing by having their exponents turn to be plus t to negative t. Your Wronskian being the same as before, only with a negative 2t instead of a positive 2t. Not terribly unexpected. Okay? So here's the part where I'm not going to skimp out on. This is now where we find our particular solution using variation of parameters. Okay? So we've got our u1. This was negative integral non-homogeneous part times your second solution from above, divide by Wronskian. So in this case, we'll have negative. Our non-homogeneous part is e to the negative t. Our second answer is t, e to the negative t. And on the bottom down here, we have e to the negative 2t. And notice, just like in our last example, this guy totally simplifies beautifully. And what is left inside that integral? Yep, just a t. So when we take this antiderivative, we'll get negative t squared all over 2. If you want to keep the constant of integration, you totally can. If you don't want to worry about it, no worries, we're not going to need it. Now, for u2, we're also going to have some awesome simplification. So we'll have an integral. We'll have f times the other solution. Make sure the subscripts don't match. So here, when we plug in, our non-homogeneous part is e to the negative t. y1 was also e to the negative t. And we divide by our Wronskian e to the negative 2t. Anybody grab what that guy simplifies to? Yep, just like before, one of them simplified to 1. So when we take the antiderivative, as I almost forgot to pull out the integral sign there, the antiderivative would be t here. Now, what does that tell you? This tells you that your particular solution is going to be u1 times y1 plus u2 times y2. So putting this all together, u1 was where? Negative t squared over 2. y1 was e to the negative t. And for u2, we have t times, where'd it go? y2. So this is t e to the negative t. T. Now this actually simplifies. Anybody got what that simplifies to? Well, the e to the t is the same in both. I should say e to the negative t. But here you've got a negative 1/2 t squared. And here, in the second term, you just have a t squared. Well, if you have negative 1/2 t squared, then plus a t squared, you're going to get, yep, positive 1/2 t squared. Okay? So that'll be your particular solution, which means when we put this all together, first, I labeled these differently than before. That was 2a. This is 2b from before. This is 3. This means our general solution, which is y, homogeneous part plus particular part, is going to be c1 e to the negative t plus c2 e to the negative t. Don't forget the t like I just did, so I tacked it in at the end, plus the particular solution, which is 1/2 t squared e to the negative t. Okay. And the only thing that we ran out of time to do after abbreviating those first two steps was plugging in the initial conditions. Quick check. If we actually went ahead and finished this problem out, what would we need to do to deal with these two initial conditions? Yep. So the first one, the y0 equals 2, you can plug in directly to this one. T equals 0 means the last two terms are going to 0 out. This e to the negative t will be 1, so that actually tells you C1 right here would equal 2. Then you take the derivative of that mess, and it's going to get nasty, crazy, complicated. Okay, not as crazy as it could be, but it'll be a mess. You then plug in t equals 0 into the derivative here. Almost all the terms will cancel out. You set it equal to negative 1, and you'll be able to solve for C2. And C2 turned out to be actually to equal 1. So the actual solution here, once you deal with the initial conditions, C1 will turn into a 2, and the C2 will turn into a 1. But I'll go ahead and post this solution, or this question solution, fully worked with the missing pieces. Okay? But that's it in terms of variation of parameters. I'm not planning on going over it on Thursday unless you guys run into questions that you want to talk about. The plan starting on Thursday and moving for the rest of the semester is dealing with Laplace transforms. For those of you going into mechanical engineering or physics, Laplace transforms you use all the time, so we want to make sure we have enough time to go over all of them. Not that you don't use the other ones, but Laplace transforms are a big deal. Okay. So any questions before we peel out of here? I know we're out of time, but I will hang out for a few minutes if you guys got extra questions.